In previous presentations, I've shown how photons of the appropriate energy making 2 revolutions per wavelength provided the basic structure of all particles. That structure gave them properties like spin, electric charge, magnetic moment, chirality, parity, duality, the de Broglie wavelength, and automatically made them subject to the special relativity corrections as they moved. That model was then applied to the structure of the only 4 known stable particles: electrons, protons, neutrons, and electron neutrinos, as well as the origins of the elementary particles, along with the structures of some of them. That was followed by a description of the principles of neutrons binding with protons to form stable nuclei. This is the big presentation. The previous talks lead up to explaining how to determine the structure and many of the properties of any nucleus of any A and Z. We are now in a position to work out the structure and properties of nuclei that make up almost all the mass of the planets. Most of the mass of the universe is made up of hydrogen and helium, which we have already covered. And yes, it's going to be done all in just one model. Along the way, I will explain a number of problems that have bothered nuclear physicists for decades. I'm going to start out where I left at the end of my presentation on the theory of nuclear binding. In it, I showed that nucleons combined in layers and discussed the structure and properties of layers containing up to 3 protons. They are all shown again here, with each layer showing the maximum number of neutrons that can be associated with those protons. For good measure, I've also shown the number of nucleons and the arrangement for 4 protons in a layer. In these and future diagrams, red represents the center of protons and blue represents the centers of neutrons. The black lines represent the proton to neutron nearest neighbor bonding. There are a number of nucleons in a layer. As mentioned in my presentation on the principles of nuclear binding, the 7Li nucleus is the largest nucleus that can exist as a single layer. The 4-proton layer, like all higher Z layers, only exists in combination with other layers. It is also shown to indicate that the addition of 1 extra proton can require 2 extra neutrons. Diagram A represents a plan view, as in the layer is viewed from above. Diagram B illustrates the same features as if viewed obliquely at an angle of approximately 45 degrees. That is used because representing all nucleons in circles will make multi-layered images far too large to fit on a slide when they get up to higher atomic number nuclei, which can have up to 8 layers or more. It is worth a second look at the Z=2 to Z=4 structures. The Z=2 structure is an alpha particle. The Z=3 structures has 3 alpha particle structures, each with a common neutron. The Z=4 structure has 5 alpha particle structures in it, of course with considerable overlap. These structures for those and other layers aren't random. The following are the rules by which nucleons can combine under this model. Within individual layers, only proton to neutron bonding is possible. The positive electric charges on the protons means they will be as far away from other protons as they can get while still binding to the neutrons. The like charge overlaps of the neutrons mean they cannot be forced too close together. Protons and neutrons within a given layer will form diamonds in a hexagonal close-packed structures. All protons in a layer will be bound to a minimum of 3 neutrons, layers with Z less than 8 excluded. All neutrons will be bound to a minimum of 2 protons. A proton can bind to just 2 neutrons in any layer in which there are no further protons outside it and no more than 3 protons in the loop. In other words, a structure in which there is only 1 neutron removed. A loop is the hexagonal structure on the outside of the 3Li structure, as shown here in this image. Rule 7 only applies for layers with atomic number less than 8. No layer can have a width of more than 2 nucleons wider than the narrowest dimensions perpendicular to it. Each outer proton can only be bound to 3 neutrons, and each outer neutron can only be bound to 2 protons. An outer nucleon is one that would be close to or touched by an elastic band stretched around a model of the layer. Neutrons can be removed from inside the lattice structure provided rules 6 and 7 are not violated, even though some of the inner protons will now no longer be bound to 6 neutrons. And that's provided that the neutron lattice vacancies do not merge to form larger vacancies than a single vacancy in a 6Li nucleus. For nuclei with Z less than 83, no layer can have more than 4 neutron lattice positions vacant. For Z greater or equal to 83, this maximum number is 3. In different isotopes, unfilled neutron lattice positions are filled from the outermost layers first. The last unfilled vacancies will be in the innermost layer or layers if there are equal number of them. Individual nucleons binding to nucleons outside those rules will form unstable nuclei with half-lives measured in seconds and usually just 1 or 2 of them. This slide shows possible structures of layers containing 1 to 17 protons and the maximum number of neutrons that can be associated with that number of protons as determined by those rules of binding. Other arrangements are possible, but they won't vary far from these. A couple of features to note are the surfaces are not regular. Apart from the Z equals 1 layer, every nucleon is in an alpha particle structure. Now you know why it's so easy to get alpha particles out of a nucleus when it is struck by another particle, and they are everywhere. They are formed in diamonds in hexagonal close-packed structures. As the number of protons per layer increases, the number of neutrons required increases even faster. I have not indicated the spins of the nucleons in each layer. Those interested in determining the full structure of larger nuclei can add them. The rules are simple. Where possible, closest like nucleons have opposing spins. Closest opposing nuclei have the same spins. Even Z and A nuclei have 0 spin. This slide shows the same arrangement of protons in the different layers, with the minimum number of neutrons in each layer as per the binding rules mentioned earlier. For ease of understanding, no attempt has been made to rearrange nucleons to take into account the missing neutron. This makes it easy to see they have formed a lattice structure where protons and neutrons have their own place in this hexagonal close-packed structure. The missing neutron positions are referred to as vacant neutron lattice positions. As I go through the structures of different nuclei, you'll be seeing that those vacancies are responsible for stable isotopes and most of those that have half-lives of a few seconds or longer. Arrangements in which there are a different number of neutrons than those indicated in this and the last slides generally have half-lives of less than a couple of seconds. There are a few exceptions to the rule, but only by a few seconds. This slide shows possible layouts for layers with 18 to 20 protons. The upper 3 show the structures with all neutron lattice positions filled. The lower 3 show the structures with the minimum number of neutron lattice positions vacant. The circle structures at the right show what the Z equal 18 layers would look like if they were shown as a plan view. The previous presentation showed that the layers of nucleons are held together by a magnetic field of the 2 layers overlapping. It is a weaker force than those between the nucleons in the same layer. All those layer structures show that they are not circular. Measurements of the shape of many nuclei will show bumps and dimples on the surface. The rules that were given earlier have been incorporated into the layers shown in this and the previous 2 slides. Determining the structure of nuclei becomes one of selecting the layers with the right number of protons for the elements of interest, arranging the layers, and then removing or adding neutrons to get the isotope of interest. This is a summary of the results of the previous 3 slides. The final column, Amax minus 2Z, is the number of additional neutrons over protons required to fill the lattice structure for the Z protons in that layer. That table should be used as a lookup table when trying to determine the structure of the nucleus of any A and Z. There are 252 stable nuclei and about 87 naturally occurring radioactive nuclei on Earth. On top of that, there are over 2,500 unstable nuclei that have been generated in laboratories. And there's no way I can handle more than a few % of them in this presentation. However, enough information will be presented that interested particles can work out the structure and properties of any one of those 2,800 plus nuclei. The rules given earlier were incorporated into the layers that I have shown you. Next is the need to follow the instructions that I will now give. A feature to note about this table is that as the number of protons in a layer increases, the number of neutrons required in that array increases at a faster rate. This presentation shows that the rate of that increase matches observation. The first step in making the structure of a nucleus is to select the atomic number of the nucleus, the structure of which you want to determine. Divide that atomic number into a number of layers, with a total number of protons per layer adding up to the Z of your interest. You should use the table in the previous slide as a guide. That is an important step. The selection should be based on making the nucleus's structure as close to spherical or oval-shaped as possible. That involves selecting layers such that the number of layers is within one of the maximum number of nucleons across the widest dimension of a central layer. Consider aluminium, Z equals 13. It can be divided into 4 layers. Layers with 3, 5, 3, and 2 protons add up to 13 protons and gives the atomic number of aluminium. Note that the widest layer, Z equals 5, has 5 nucleon layers across it. That means the aluminium nucleus needs to have at least 3 layers. Take the image of the different layers from those with all of the neutron lattice positions filled from those previous slides. They are shown here as side by side in a plan view. All future images will be shown in the 45-degree oblique view with the layers stacked vertically above each other. That represents the layout of the isotope 30Al. Its minor claim to fame is that it represents the highest mass number aluminium isotope that has a half-life of greater than a second. The importance of that will become apparent later. The next step is to arrange those layers in order and start subtracting neutrons until they get the isotope of interest. This slide shows all the possible aluminium isotope structures under the rules of binding given earlier. We will start at G, isotope 30. It has a half-life of 3.6 seconds. There is obviously an excess of neutrons. Removing 1 neutron gives F, which is isotope 24 and has a half-life of 6.5 minutes. Removing 2 neutrons gives 28 Al and a half-life of just over 2 minutes. It seems to be a very good trend that nuclei with odd Z are more stable with even numbers of neutrons. 27 Al is stable. 26 Al is shown as in 2 forms with 2 different half-lives. It is suggested that the upper diagram represents the more stable form. The lower image, which has 1 layer with 2 protons per neutron, has about the same half-life as the 25 Al, which has 1 2He layer. That is as low as the 4-layered Al isotope will go under this model. The rules of binding allow for a 5-layered structure, as is shown in A. Its feature is that its half-life is still above 1 second. The importance of that is that the rules of binding give isotopes with stable nuclei or those with half-lives longer than about a second. From here on in, I'll refer to them as quasi-stable nuclei. Image J shows the spins of the different nucleons in the 27 Al isotope. The number to the left of image J shows the residual spins. The number to the right shows the residual magnetic moment of that layer. Together, they predict that the spin of the nucleus will be 5 halves, and the magnetic moment should add up to 4.55, etc., mu BP, where mu BP is the Bohr magnetic moment of a proton. 27 Al's magnetic moment is 3.64 mu BP. Not far, but it just indicates that some slight alteration to the radii of the rotating photons of the nucleons that make up the nucleus. That gave a brief introduction on how to work out the structure of nuclei under this rotating photon model of matter particles. There are a number of other aluminium isotopes that have been produced in particle physics laboratories. It is time to have a look at them. But before doing that, I'm going to remind you again, it is worth a quick glance at the image of the 30Al isotope. With all neutron lattice positions filled, every nucleon is part of an alpha particle structure. And just keep your eye out for that, because as I go through those structures of other nuclei, you'll just find alpha particles everywhere. The best way to start explaining these unstable aluminium nuclei is to again start with the 30Al isotope, which is diagram G. All protons are already well bound to neutrons. There are no sites where two protons can capture a neutron. The only way for additional neutrons to bind is for their negative n/27 harmonic to overlap a proton's positive charge. There are 12 easily accessible protons on the outside of a nucleus. A neutron can easily access one of those 12. There are no sites available where a neutron can access two protons. Now, diagram K shows the situation of one neutron binding to one easily accessible proton. It could be any one of them. Its half-life is less than a second. Diagram L shows a situation where 6 of the available protons have been captured by a neutron to form 36Al. Its half-life is measured in milliseconds. In the presence of excess neutrons, the process continues until all available protons have captured a neutron. The half-lives of the isotopes will progressively diminish with slight deviations due to the even and odd number of neutrons. If they exist, lifetimes of isotopes 40 and above is quite short, typically less than 1 millisecond. It is questionable whether a neutron could bond to the inner protons, indicated by the orange ellipse in the middle of M. After that, there is nowhere else for neutrons to go. It will be shown later that isotopes where neutrons can access more than 10 exposed outer protons are rarely, if ever, detected. At the other end of the scale, start with the 24Al quasi-stable isotope and subtract a neutron from one of the 3 hexagon ring structures. One hexagon ring becomes an alpha particle with a proton weakly attached to it in the isotope 23Al. That is shown in diagram N. One proton is bound to one neutron, it's caught up by the neutron's n/27 outer oscillation. It's like a satellite nucleon, very unstable. Its half-life is 470 milliseconds. Remove another neutron from another hexagon ring and another alpha particle structure with a proton weakly attached to just one of its neutrons is the result. That structure is shown in Q. It has a half-life of 92 milliseconds. Can another neutron be removed? Removing one offers a couple of possibilities. One is that the excess positive charge repels at least a proton and the structure is no longer an aluminium isotope. Another is that it is too difficult to add a proton to a 20 mg nucleus, which itself only has a half-life of 90 milliseconds. In any event, has not been detected. I should point out at this stage, you don't actually take neutrons out of a nucleus. In order to form those nuclei that I've just mentioned, you have to start out with lower Z nuclei and add protons to them. That is as far as I'm going to take this structure on aluminium as an example of how to work out the structure and properties of nuclei of different A for a given Z. Under the rules of binding, other structures for those nuclei are possible. A good way of working out what they are is to look at the decay products of radioactive nuclei. It is suggested that different structures of the same isotopes will give rise to different decay products and/or half-lives. I hope it is realized there was nothing difficult about that approach. I have concentrated on the structure. Dimensions of the structure can be determined from binding energies, as was done for the isotopes of hydrogen, lithium, and carbon. Those interested in spins and magnetic moments of nuclei can follow the procedure also given with the structure and repeated for aluminium. Without additional computing power, spins are more easily matched to measurements than are predicted. Of course, that doesn't apply for nuclei with even A and even Z. They will always be spin zero. The spins reflect magnetic moments, but they have a slight variation for the changes to the structure of the rotating photons that are producing them. A 3-4-4-2 layer approach yields similar results. Distinguishing between the two would require measuring the dimensions of 27 Al nuclei. There is also the possibility that nuclei may be a mixture of both structures. And what else do you want to know about aluminium isotopes that can't be worked out by that mechanism? Now, that approach can be applied to any other Z and A combination. There's nothing difficult in it, but it can be tedious when done manually. From now on, I will just present the results obtained with a few different selected examples of nuclei. This slide shows some selected structures of different oxygen nuclei. With 8 protons, a 2-3-3 proton layer fits the requirements. The 13O isotope has 2 protons in the alpha particle layer outside the rules of binding. It is a short half-life time. The binding is shown by lighter bonding lines that represent that different bonding. Normally, I would expect the lifetime of such a structure to be less than a second. With the same spin on both protons and neutrons, they can get additional magnetic binding and have a slightly longer half-life. The most abundant isotope, 16O, has both its hexagon rings with a vacant neutron lattice position. The 18O isotope is stable and has all neutron lattice positions full. As you can see, its 8 protons are on the outside of the structure. That allows up to 8 neutrons to be positioned onto the oxygen 18 isotope. The added neutrons are illustrated as lighter blue ovals with a light grey line joining them to the proton. The 20O isotope is in the same situation as the 13O isotope, with both protons and the neutron to which they have attached having the same spins. There will be additional magnetic binding that helps to give it a half-life of over 10 seconds. The 24O isotope has a short half-life of about 60 milliseconds. There are so many additional neutrons that the same spins aren't going to help produce a longer half-life. The 26O isotope is the end of the line for additional neutrons because there are no more positions where neutrons can attach to the nucleus. It has been detected, but its half-life was not known when I first studied it. In case any doubters think this is a bit fanciful, there is an easy way to check it out. Note that the charge is distributed around the outside of the structure. So all you've got to do is measure the charge distribution of oxygen nuclei. It should show a decreased charge density near the center, rising to a maximum charge density at about just over 1 FM. Oh, look, it's already been done. Hofstadter's results are shown in this plot on the right. The red arrow and O draws attention to a line with an O on it that is heading up from about 1 unit of charge density, measured in terms of 10 to the 19 coulombs per cubic centimeter, to about 1.25 at about 1 to 1.2 FM. But that's not the only one. The red arrow with a C draws attention to a line marked C. It is for carbon. It rises from just under 1.25 times 10 to the 19 coulombs per cubic centimeter to a slightly higher maximum, again at about 0.8 FM. As derived in my last presentation, its structure is shown here. When you look at the structures of the carbon and oxygen nuclei under this model, it seems to fit quite reasonably. I'm going to be bold enough to suggest that this is not coincidence. It's been occurring because that's their structures. Note also that the long tails of all of the nuclei shown in this diagram. The insert at the bottom left, also from Hofstadter, shows the charge distribution of nucleons tailing off over some 2 femtometers. It is not too dissimilar to that shown in the nucleon charge density curves. It is that tailing off of the charge density of individual protons that produce a tailing off that is measured in the nuclei. That is the cause of the nuclear skin effect that has bothered standard model nuclear physicists for decades. This slide shows some of the isotopes of neon, Z equals 10. The isotopes from 19 to 23 all obey the rules of binding. The most abundant isotope, 20 Ne, has 3 internal neutron lattice positions vacant. The low abundance of the 21 Ne isotope is yet another example of how odd numbers of nucleons are not good for nuclear binding. The 22 Ne isotope has much greater abundance than it. The 23 Ne short half-life again indicates that odd numbers of nucleons are not good for binding. The additional neutron in the 24 Ne isotope indicated by the pale blue oval is outside the rules of binding because it is attaching to outer protons that already have 3 neutrons binding to them. It is one of the few exceptions when neutrons in that position give half-lives more than a second or 2. When it decays by beta emission, the structure rearranges itself and finishes up as 24 Mg after transiting through 24 Na. The 24 Ne isotope still leaves all 10 protons external and available for neutrons to temporarily attach to them. 34 Ne is the highest atomic number neon isotope detected, and there are no more sites to which neutrons can attach. The next nucleus I discuss is calcium, Z equals 20. It is interesting for a number of reasons. In one way, it represents a transition from low Z nuclei to high Z nuclei. It, like the multilayered even Z greater than 2 nuclei before it, has its most abundant isotope with all its internal neutron lattice positions vacant. Odd Z nuclei with Z less than 20 have 1 internal neutron lattice position filled and the rest vacant. Calcium has a large number of isotopes, 6 in total. There is some suggestion that 48Ca is unstable with a half-life of over 10 billion years. In my language, that makes it pretty stable. I have used a symmetry of 2, 3, 5, 5, 3, 2 protons per layer in this study. Another feature to note is that in order to maintain the rules of binding required for the 48Ca isotope to be stable, it was necessary to rearrange the number of layers and the nucleon arrangements within them to a 4, 6, 6, 4 protons layer arrangement. That is not unusual among the higher Z nuclei. The 38Ca nucleus is within the binding rules. Its half-life is a little lower than 1 to 2 seconds. On the other hand, you can't take 8 neutrons away out of the 48Ca nucleus and have it remain inside the rules of binding for 40Ca. That is why the 40Ca nuclei and some of the higher Z nuclei can only have the 2, 3, 5, 5, 3, 2 layer structures indicated. The highest A calcium nuclei have the 4, 6, 6, 4 proton layer structures. This serves to show that layers of different isotopes of the same element can have different layer structures. That brings us to another feature associated with isotopes of higher Z nuclei. Isotope Ca50 obeys the binding rules. It has 18 external protons to which neutrons could temporarily bind through their negative n/27 harmonic oscillations. That could allow an extra 18 neutrons to bind to the 50Ca isotope, making 60Ca the highest atomic number calcium isotope. In practice, it doesn't work that way. By the time an additional 10 neutrons have been added, the nucleus is so unstable that additional neutrons can't be added any faster than the existing neutron-rich nuclei decay to a higher Z element. Adding additional 10 neutrons beyond those allowed under these rules of binding is all you can do with the addition of more neutrons to form higher A isotopes. 60 Ca is the highest atomic number calcium nucleus listed in isotope tables. The next nucleus of interest is iron, atomic number 26. Its interest comes from two main reasons. Commercially, iron is the most widely used metal in industry. Scientifically, the iron isotope, 56Fe, has the highest binding energy per nucleon of all nuclei. This slide shows some selected iron isotopes. Those from 52 to 62 obey the rules of binding. The 51Fe isotope has a half-life of about 300 milliseconds. That is as expected because it's outside the rules of binding. The isotope 64 has 2 neutrons in excess of binding rules. Again, if their spins are the same, they could have a half-life of over a second. The Fe62 isotope has all neutron lattice vacancies filled. Extra neutrons can only attach loosely to 10 of those protons before their rate of decay reaches the rate at which new neutrons can be added. The isotope 72Fe is the highest mass number Fe isotope detected. Even then, its half-life was measured in nanoseconds. The other feature to note is that the most abundant isotope, 56Fe, has only one of its internal lattice positions filled. The next element I discuss is palladium, atomic number 46. It is halfway up the periodic table of naturally occurring elements. This slide shows all stable palladium isotopes. As expected, all comply with the rules of binding given earlier. The lowest stable isotope, 102Pd, has 11 vacant neutral lattice positions. The most abundant isotope, 106Pd, has 4 of those vacancies filled. The preference for even Z and A nuclei is seen in Pd 105 being the only stable palladium nucleus with an odd number of neutrons. 107Pd, also adjacent to the most isotope 106Pd, has a half-life of over 6 million years. It is still radioactive. The highest atomic number stable palladium isotope, 10Pd, has 3 neutron lattice positions vacant. It is now time to look at the structure of some of the radioactive palladium nuclei. They are shown here with a 2, 5, 10, 12, 10, 5, 2 proton layer structure. The isotopes 96 and 100Pd are still within the binding rules. 96Pd is the lowest mass number that complies with this structure. Variants of the 95, 94, and 93 isotopes have half-lives up to 10 seconds, somewhat at odds with my earlier statement about having half-lives of less than 1 second. I have not checked to see if other variations, that is, different layers and structures, would fulfill that requirement. Note that I refer to variants of those radioactive nuclei. The same isotopes often have different decay modes and half-lives. It is suggested that occurs because there are different structures of the same isotope. That would usually be a different number of layers for the same isotope in the same element. The different structures would have different stabilities. That should be easy enough to check out by using another combination of layers. The 113Pd isotope is the highest mass number that fulfills the rules of binding for that chosen geometry. Its half-life is over 90 seconds. It has a lot of positions where additional neutrons can temporarily bind. Isotopes 118 and 119Pd have a few sites occupied. Their half-lives are either side of 1 second. It would therefore not be surprising if the addition of 10 further neutrons formed the highest mass number palladium isotope. And that is what is found. Adding 10 neutrons to the highest A isotope with a half-life above about 1 second is the limit that can be added. The isotope 129 PD is the highest mass number isotope that I have found in the list of palladium isotopes. Palladium also represents a transition between lower atomic number elements and the mid-range elements either side of tin, atomic number 50. Tin has 10 stable isotopes and over 40 isotopes altogether. Its most abundant isotope, at almost 1/3 of its composition, is isotope 120. It's also in the middle of the range of isotopes, which extend from 99 SN to 139 SN. Is also where about half of the vacant inner neutron lattice positions are filled. In all nuclei up to palladium, there were more isotopes and stable isotopes above the most abundant isotope. The most abundant isotope is generally the one with the highest binding energy per nucleon. After tin, there are more isotopes below the most abundant isotopes. To show why, I'll go straight to lead, atomic number 82. The answer to many questions is found in the 208 Pb structure. It is shown here with 8 layers of nucleons containing 3, 8, 12, 18, 18, 12, 8, and 3 protons respectively. Its important feature is that all the neutron lattice positions are full. It is the end of the line to stable nuclei. Another feature to note is that every nucleon in all of those stable isotopes is arrayed in an alpha particle structure. That helps explain why it is so easy to knock alpha particles out of nuclei. They are everywhere. Adding the statutory 10 neutrons takes the mass number to isotope 218, which is about the heaviest Pb isotope registered. There is plenty of room to reduce the number of neutrons. The 190 Pb isotope is the lowest mass lead isotope that obeys the rules of binding. Its half-life is just over 1 minute. There are about a dozen lead isotopes of lower mass number where more neutrons have been removed. They all have half-lives significantly less than the 190 Pb. Some half-lives are measured in units of seconds, others in milliseconds or smaller. I admit that it is a long exercise to go through and work out the strengths of each of the about 300 proton to neutron nearest neighbor bonds, as well as those of the about 150 second nearest neighbor bonds to work out the dimensions of large nuclei like Pb208. But there are plenty of formula that can give reasonably accurate predictions. It is easy enough to do the reverse. Count the number of neighbor and nearest neighbor bonds, and then using geometry, you could work out the average binding energy per nucleon in each layer. That involves an assumption of the magnetic binding energy per nucleon between the different nucleon layers. I have chosen that at 0.8 MeV per nucleon. Similarly, 208 Pb's spin and magnetic moment are much easier to calculate. With even numbers of protons and neutrons, both will be 0. That should also put paid to the idea that nuclei en masse rotate to give a nucleus a measurable spin. Nuclei can't and don't rotate. The spin of all nuclei is the sum of the spins or the angular momentum of each individual nucleon within it. Not shown here is that 209 Pb has another arrangement of layers obeying the binding rules. It is virtually stable with a half-life of 10 to the 18th years. This slide summarizes the results of the model as it has so far been presented. It has been extended up to atomic number 100. According to the rules of binding, the blue dotted line represents the maximum atomic weight A for a given atomic number Z. The red dotted line represents the minimum atomic weight for a given atomic number. For atomic numbers below 50, those lines represent the limits of stable and quasi-stable nuclei, where quasi-stable means those with a half-life of greater than a few seconds. Above Z equals 50, there starts to be a few nuclei that have some half-lives greater than a couple of seconds. and they exist outside those lines. Some even last for a minute or two. It is possible, but I haven't checked, that that is due to them having different structures than those that I have presented. The most abundant isotope of an element is generally determined by those with the highest binding energy per nucleon. Up to Z equals 20, all even Z most abundant nuclei are on the minimum A for a given Z line. They correspond to all internal neutron lattice positions being vacant. In the same range, all the most abundant odd Z nuclei have only one internal lattice position filled. Above atomic number 20, the most abundant isotopes slowly change from the minimum A for a given Z to the maximum A for a given Z by the time Z equals 82. That PB208 represents the end of the line for stable nuclei, is dictated by the lattice structure of the layers and these rules of binding. It doesn't have to be artificially introduced. There is no other way. Tin, Z equals 50, is the nearest even number to the middle between Z equals 20 and 80, which corresponds to the higher atomic number nuclei. It has the greatest range of nuclei either side of its most stable isotope. It has 10 stable isotopes, the greatest number of any element. The number of isotopes above and below the most abundant element also changes around Z equals 50. At lower Z, there are more isotopes above the most abundant element. At higher Z, there are more isotopes below the most abundant element. They are predictions of this model. They also coincide with observation. I have not overlaid experimental results on this plot. That is left to nuclear physicists. They may be surprised about how good this theory matches observation across nuclei of all A and Z. Another element of interest is uranium. 4 of its isotopes are shown here. They are shown with 8 layers containing 3, 9, 14, 20, 20, 14, 9, and 3 protons respectively. As expected, the most abundant isotope, 238U, has all neutron lattice positions filled. The isotope 235U has 3 neutron lattice positions vacant. They are shown here in one of the central layers. The 2 other isotopes have progressively more neutron lattice position vacancies and progressively shorter half-lives. With all nuclei above 208 Pb already being radioactive, it would not be surprising if it was not possible to add 10 neutrons to 238U nuclei. The highest A uranium isotope made in a laboratory is about 243U. It is also what happens to the U235 isotope that is of greatest interest. This slide shows some detail about the 235U isotope. Diagram A is the same representation as given in the previous slide. As mentioned in the binding rules, neutron lattice vacancies are filled from outside in. The last 3 neutron lattice vacancies are shown in one of the middle layers. The line M indicates the separation of the 2 middle layers. The line H represents the partition of the layers with the lattice vacancies through a passage. It also involves severing of 5 proton to neutron bonds, the smallest number in this configuration. An incoming neutron initiates the fission. The fission process is an intra-layer phenomena, not an inter-layer one. In this presentation, the split along H sends those in the line above H into the upper layer, as shown in the elliptically enclosed diagram B. That gives isotope 134 Te. The residual isotope is 101 Zr. Both are before the emission of 2 neutrons, which together with the original neutron means the fission event must include the release of 3 neutrons. It is the extra neutrons that then, of course, allow the fission to continue on in a chain reaction process. Equally, the larger segments could have stayed with the upper layer to generate the 155 Nd60 isotope and the 80 Ge30, again from which 2 neutrons must be subtracted. Diagram C suggests a scenario in which 3 protons and 4 neutrons separate from the lower central layer that has the 3 neutron vacancies. In the configuration shown here, that requires the breaking of 6 proton to neutron nearest neighbor bonds. When they stay with the other 3 lower layers, it gives the isotope 74 Cu. The remaining group gives isotope 161 EU63. Both are before the ejection of the 2 additional neutrons. Apart from splitting totally at the whole layer, that represents the extremes of the fractions that can be generated in the fission of this 8-layer structure. Other lattice vacancy positions would allow other fractions to be generated. The upper layer in all 3 diagrams are half of 238U isotopes, giving them a mass number of 119. The middle layer that has the neutron lattice vacancies has mass number 29. If its most probable fission is half of that 29, it would add mass number 15 to the upper layer, giving the most probable heavy fraction a mass of about 136 atomic mass units. That would leave the most probable light fraction with a mass of about 101 atomic mass units. Take 2 mass units away for the 2 neutrons that would be emitted from the most probable light fraction, and it would give a mass of 99 atomic mass units. What has been described earlier is basically what is shown here in this extract from the work of Weil. This model suggests peaks around 99 and 134 mass units. It suggests a minimum mass fraction at 74 and a maximum fraction at 161. The odds of getting a split straight down the middle, where the vacancies are on one side of the middle, are not good. The model has all the main features of this plot. It will require more work, of course, to see if the model's trends match the observed distribution, but that's a task somebody else can undertake if they wish. I started out this presentation pointing out that I would offer a model that would match the structure and some properties of any nucleus of any A and Z of choice. Together with the principles of nuclear binding, I have covered some of the nuclei from deuterium all the way up to isotope 238U. In this presentation, I concentrated mainly on the structures and the isotopes of a few elements, both those occurring naturally and those produced in laboratories. That included how their structures influence some of their properties like stability. The following is a brief summary of this presentation. Within a nucleus, nucleus align themselves in planar hexagonal close-packed layer arrays. Except for nuclei with Z from 1 to 3, all other nuclei are multi-layered. Within those planar layers, the only bonding is between protons and neutrons. Protons are as far away from each other as possible. The nucleons form alpha particle structures. The layer structure means the number of neutrons required to hold the protons together increases faster than the number of neutrons in the layer. The strong nuclear force is due to neutrons' negative charge segments overlapping protons' positive charge segments at very short separation distances. I've called that division by zero attraction. It is supported by nucleons arranging their spins so as to give maximum binding within each layer. The layers are held together by the magnetic field of the nucleons. It is weaker than the binding between protons and neutrons within individual layers. Rules were given for how nucleons could combine within the layers and how the layers would assemble. Those rules were applied to isotopes of selected elements from deuterium to uranium. Overall, there was a good agreement between theory and observation across that whole range. I believe the agreement could be made better if different layers were chosen for some of the isotopes where the agreement wasn't all that good. Nuclei of the same Z but with different A can have different layer structures. Isotopes of higher Z nuclei with the same A can also have different layer structures. They show up by the same isotopes having different decay modes and/or half-lives. That agreement has solved a number of issues that have concerned nuclear physicists for some time. These include, but were not limited to, a single model that covers all isotopes of all nuclei, an explanation of the skin effect of why the charge density of all nuclei tailed off over a couple of FM, why PB208 is the highest A and Z nucleus that is stable. It also provides support for the icing model that gave a good explanation for the fission of the 235U isotope, the origins and structure of different isotopes associated with all the elements. It explains why they are there and what their properties can be. It explains why A equals 5 and 8 nuclei cannot be stable. It also explains why the strong nuclear force is so strong and yet has such a limited range. It also shows why a lot of nuclei are not spherical. The 12C nucleus is an equilateral triangular shape. Larger nuclei can have dimples and bumps on their surface, and that has been measured. The best summary I can give is to say that this whole presentation was a summary of what this rotating photon model reveals about the structure and properties of nuclei. I have not given a mathematical derivation of the strengths of the binding forces. Instead, I have used that trusted mechanism of fitting curves to experimental points. I have laid down a few rules and used those rules to derive some of the properties across a wide range of atomic and mass number nuclei. For those interested in knowing the structures and properties of other nuclei, I've reduced it to an exercise in geometry and counting. After all, there's only a limited number of nucleons in any nucleus. They are added. There is still plenty of scope for determining other geometric layouts within those rules of binding and other variations. It is my opinion that this model is able to replace all other nuclear models. So that shows how to determine the structure and properties of nuclei. There is still a lot more to be done before we can begin to understand just the planets in our own solar system, let alone the rest of the universe. The next step is to show how nuclei fuse to have their relative abundances. Then we have to put electrons around them to form the atoms. And that needs to include the properties of electrons that cause them to bind the atoms together to form all the materials we have around us. Then we can get on to describing gravity and the rest of the universe.